Welcome back for part 2. If you've not watched part 1 and you're not very confident that you already know all the definitions I'm likely to use, I would recommend going and watching part 1, but you do you. We'll see how we go. So yeah, in this talk, I'm going to tell you about the class of groups that we worked with and tell you about how we went about using the chief alpha rebuilding property to prove that the homology growth vanished in all of these. So as a very quick recap, G is always finitely generated and residually finite. We're trying to say something about the behavior of the homology of G as we take a sequence of finite index subgroups. We have to look at the homology of those finite index subgroups and see what happens. And we're going to use this cheap alpha rebuilding property due to Aber, Bergeron, Frazik, and Gaboriel to conclude that there's no growth, or if we're looking at the size of the torsion parts, maybe what we're concluding is that whatever growth there is sub-exponential. And this property is useful for us because it's designed to be used for piecewise inductive kind of arguments on CW complexes with actions of your favorite group. So it's a very useful tool for figuring out that you have no homology growth. And the groups that I'm going to be talking about are what's known as mapping tori. So the mapping torus of a group G that I began with over some automorphism phi is a semi-direct product, G semi-direct Z, where the action of Z is given by phi. So playing perhaps slightly loose with group presentations, we're going to take G, imagine I have thrown in whatever relators I needed to throw in, perhaps the multiplication table, and add one extra generator T, and I'm going to say that when I conjugate any element of G by T, I see whatever phi did to G. This is going to be a perfectly well-behaved group, and it actually doesn't, I can vary the automorphism a bit without changing the group I get. So if you know what the outer automorphism group is, then this is actually only depending on picking an outer automorphism. And sometimes I might be slipping up and using capital phi's, which means I haven't picked a representative necessarily. Here's a lemma to convince you that I'm not saying complete nonsense. I'm not going to prove it, but I am going to assert it. If G is finitely generated and residually finite, then so is this mapping torus, whatever phi I picked. And you can find counterexamples dropping residually finite, it passes to subgroups. Of course, you can find counterexamples, but if you drop finitely generated, there are counterexamples as well, because you need to, it uses the useful fact that there's only finitely many subgroups of a given finite index in a finitely generated group. So we can ask the questions that I was describing in the first part of the talk about how things behave as we take a sequence of finite index subgroups that intersects trivially. And saying everything about every group that arises this way might be too much, but I'm going to tell you about some conditions on G and on phi that are going to allow us to say something about how the homology grows or doesn't, as the case might be. Okay, so here is the theorem, due to me, Yassine, Sam, and Monica. Gamma is going to be a residually finite group isomorphic to a mapping torus of some kind. The first option is that G is hyperbolic, or more generally hyperbolic relative to a finite collection of virtually polycyclic subgroups. The second option is that it's a right-angled Artin group, and there's some extra conditions on phi here. And finally, it could be a right-angled Coxeter group. If the automorphism is polynomially growing, which is a definition that is about to occur, then for every Faber sequence, this is like a more general version of taking a sequence of finite index subgroups that intersect trivially. Every dimension I might think to look at, in every field, we have these limits, the one capturing how the dimension changes. If I pick homology with coefficients in some field, how the dimension changes with the index. The other one looking at just the size of the torsion part, but taking logs and then looking at how that changes, then both of these limits vanish. Okay. So I need to tell you what polynomially growing automorphism is. And for this, we need, I guess, one step back's worth of definition. We're going to have a finite generating set for our group. And I'm going to take my element G, and I'm going to look at its conjugacy class. And some representative in that is going to be shortest. Several, maybe you can kind of do a cyclic permutation thing. And this is over natural numbers. So there is a shortest, whether it's constructible. If you give me a particularly bad group, maybe not, but something's shortest. And we're going to take the word length. And then this is really a definition for outer automorphisms, so it doesn't mind if I do conjugating after I apply my automorphism. So I'm looking at the conjugacy class. An outer automorphism is polynomially growing if in any generating set, doesn't matter which, there's some integer, the degree of the polynomial, and some constant, probably quite large, so that as I iterate the automorphism, taking the shortest representative of the conjugacy class each time, this sequence is bounded by a polynomial of degree d. So I have some examples. The first example is polynomially growing. I didn't say which group. These are in the free group of rank 2. Maybe some other groups as well, but I don't know what the growth necessarily looks like. So the first one, A goes to A, B goes to BA. Definitely an automorphism of F2. And we can look at what happens to A as we iterate, and the answer is nothing very interesting, just stays A. We can also look at what happens to B as we iterate. Something slightly more interesting. It goes to BA, goes to BAA, goes to BAAA. Every time we add another A on the end. So these words are length 1, length 2, length 3, length 4. This is going up linearly. This has linear growth. That wasn't a proof. I could have been hiding something somewhere, but I wasn't. This automorphism genuinely has linear growth. Here is a non-example. The non-example is also living in the automorphisms of a free group. And it looks, on first glance, quite similar, but it's not. A goes to B, B goes to AB. So I've started swapping things around. This is where the bad behavior comes from. I only need to look at what happens to one element because A goes to B, keeps going, so I've captured all of the generating set already. A goes to B, goes to AB, I said that in the definition, goes to BAB, AB, BAB, BA, BA, BB, AB. Reading out increasing sequences of A's and B's maybe not super useful, but we can look at the lengths. They go 1, 1, 2, 3, 5, 8. The next one is length 13, and the one after that is length 21. And I have smuggled the Fibonacci sequence into my talk because this is the easiest way I know to convince people that a sequence is exponentially growing. Hey, look, it looks like the Fibonacci sequence. This has exponential growth. This isn't bounded above by any polynomial in any degree. So we don't want to consider things that look like this. We want to consider things more like the first one. And how are we going to go about proving this theorem? I've lost the Z. Oh, well. We're going to show that G semi-direct, there should be a Z there, with the defining automorphism polynomially growing has the chief alpha rebuilding property, and we're going to get it for all alpha. And we're just going to use actions on trees. We don't need CW complexes in higher dimensions. Trees will do, and we're going to show that these satisfy the conditions that we needed. These are actually easier if you restrict to trees, it turns out. So gamma is going to be residually finite, alpha some dimension. Suppose gamma acts on a tree co-compactly, so the quotient is finite, and without inversions. Subdivide every edge, it's definitely without inversions now. If every edge and vertex stabilizer has the cheap alpha rebuilding property, then so does gamma. I could have only forced edges to have alpha -1, but edges aren't our problem and we're going to get it for all alpha. So I've taken the easy way out. So we're looking for actions on trees where we understand the stabilizers, understand meaning we know they have this property, and we're also allowed to pass to finite index subgroups whenever it makes our life easier. We're going to investigate quotients by groups which have the cheap alpha rebuilding property, and whenever we see a free abelian group, we're very happy. We win. So, where am I going to come up with my actions on trees? The answer is I'm going to begin with a group which acts on a tree somehow, and every time I do this and I have an automorphism, I can get another action of the same group on a tree. The easiest way to see this is to remember that group actions are secretly homomorphisms into the automorphisms of whatever object you're acting on. In this case, a tree by isometries with the path metric. So yeah, I do my automorphism, then I do whatever homomorphism I first thought of. I came up with another one. Sometimes, not usually, but sometimes, the resulting action is equivalent to the one that you first thought of. The right definition of equivalent here is equivariantly isometric. It's a bit difficult to get your head around, maybe. But it's the right notion of equivalence in this sense, and it says that if I look at how an element acted to begin with and how it's acting now, these are similar. They've maybe moved around the tree, but in a way I can capture with an isometry. In particular, if it was translating along an axis, it had better still be translating by the same amount along an axis somewhere. And there's a useful proposition which is kind of alluded to in Culler and Morgan's work. I often think of it as a lifting property. If I have an automorphism which is fixing an action, then the action extends nicely to an action of the mapping torus. What do I mean by nicely? I mean the G that you began with and the G you see there are the same ones. So this is handy. We're going to use this to find actions of a tree, actions of G on a tree, and automorphism that plays nicely with them. And then we're going to use that to get an action of the mapping torus on a tree. And that action is going to be the one that tells us about the cheap alpha rebuilding property. So there's sort of two steps to our proof. There's a free product step, which is an induction, and there's a step to get the base cases sorted. And I'm somehow talking about these in the wrong order. I'm going to talk about the induction first, and then after that, I'm going to go on to the base cases. So for free products, we want to get an induction going. The base cases are going to be freely indecomposable groups. I'm going to throw Z in that class. And these are the groups which I can't have no interesting free product decompositions. And I'm going to assume for now that I've done the base case. Or I guess what I really mean is I have restricted to a class where whatever free factors I see are behaving nicely. So if I'm not a freely indecomposable group, then I have a Grushko decomposition. I can rewrite G as a free product of some GIs and a free group. And I'm going to demand that the GIs themselves are freely indecomposable. I can't split them up anymore. And they're not going to be infinite cyclic. I want the infinite cyclic bits to be living in the free group at the end. This decomposition is canonical in the sense that if you try again, if I mess up the presentation and hand it back to you and you try again to get a Grushko decomposition, you end up with the same rank free group at the end. The things generating it might have changed, but the rank is the same. And up to conjugacy, you see the same free factors GI. So they might all have been conjugated by different things. There are some constraints on what you can do, but different conjugators are definitely possible. But up to that indeterminacy, you see the same set of free factors. It corresponds to an action on a tree, but unfortunately it corresponds to a lot of actions on trees in general. And all of these actions have trivial edge stabilizers. This is to do with being a free product, but because there's so many of them, there's usually no way to say that they're preserved by my favorite automorphism, or even a power. Passing to powers is passing to finite index subgroups. It often gets you out of trouble, but in this case, no such luck. We're going to induct on what's called the complexity, so the number of free factors plus the rank of the free group, to get us out of this annoying situation where, while we have something canonical, there are too many actions on trees. So how does this go? If phi is polynomially growing and it preserves some free decomposition, then I can find a power. So the power preserves a decomposition either as H free product with K or as H free product with Z. And these are much simpler. And each free factor of my original decomposition is conjugate into one of the H or K going on here. Is sort of what's happening. What makes this go is north-south dynamics on the right free factor complex. If you fail to do this, then you can cook up some exponential growth. So we look at the actions on trees dual to these splittings, and because they're much simpler, these are actually preserved by every automorphism, preserving H and K, and that means that we get an action of gamma, the mapping torus, on a tree with vertex stabilizers that again look like mapping tori. I'm playing a bit fast and loose with what phi is doing. I've passed to a power and I've also restricted it to a subgroup. And the edge stabilizers are going to be Z. This is a general property of how these actions change, is that I'm still seeing all the stabilizers I saw before, and because I have this quotient to Z, then lifting things back works nicely. H and K probably split themselves as free products, but the complexities are lower. If the complexity could have stayed the same or gone up, then something went wrong with the uniqueness of my Greshko decomposition. So we used the inductive hypothesis to finish. So I've assumed inductively that I could do it for lower complexity, and I've split up, so I've got some lower complexity around, and then I can use the fact that I understand it for lower complexity to finish, use the proposition or the theorem about actions on trees, and say, hooray, we have cheap alpha rebuilding property. Now I need to do something with the base cases. And I actually need some of the hypotheses I had to begin with. This free product argument is kind of very general. As long as under the groups that you allowed to be free factors behaving, you can use this free product argument. So if G is hyperbolic and torsion free, this is more restrictive than the theorem, but it's easier to explain, and not infinite cyclic, and doesn't split as a free product. It's one-ended. It's a property that groups can have, and this means all of what came before means that it has a canonical JSJ decomposition. This is an action on a tree which we like. We understand it well. Useful things to currently know: the edge groups are infinite cyclic. The vertex groups come in 3 flavors in this exact situation. They're either infinite cyclic, they're free groups, somehow correspond to punctured surfaces, and the other thing they might be is rigid, which sort of means none of the above, but it means none of the above, and they don't have very many automorphisms. And that's extremely useful. And why this is useful is that one of the things that canonical means in saying it's a canonical JSJ decomposition is that it's preserved by all automorphisms, including whatever phi we cooked up. So we get an action of the mapping torus on a tree, and we can use this to get at the cheap alpha rebuilding property. So we lift the action to the mapping torus, and we see the same kind of options for stabilizers again. Maybe we have to pass to a finite index subgroup, but that's okay, we're allowed to do that. Edge groups wind up being z squared. Great, that has the cheap alpha rebuilding property for all alpha. Vertex groups might be z squared, again, great, happy days. They might be free bicyclic with a polynomial automorphism, and somehow this automorphism knows that there was an underlying surface, so it's even more restrictive than that. Or they might be rigid times cyclic. The fact that I've got times is a consequence of one of the things I did when passing to a finite index subgroup, and the fact that these have finitely many outer automorphisms, or finitely many allowable outer automorphisms at least. So as I said, the z squared stabilizers are good, happy days, we can deal with them. I don't want to go into the details, but we can deal with the free bicyclic stabilizers, take another decomposition. And the underlying hyperbolicity assumption means that the rigid groups are type F infinity, they're type F alpha for every alpha. So taking the Z as the normal subgroup with the cheap alpha rebuilding property, the quotient is R. This has the finiteness property that we need. And these have the cheap alpha rebuilding property. So by the theorems, so does G. Happy days, we win. And I want to say a couple of words at the end about the other bits of the theorem that I didn't say anything about yet. Torsion, relative hyperbolicity, right-angled Artin or Coxeter groups. If you allow torsion, but you still said residually finite, then the decompositions you see aren't quite as nice, but you can get yourself out of trouble by applying a few more finite index subgroups. The same arguments end up applying. That's very, very briefly how that works. Relative hyperbolicity, again, makes the decompositions more complicated, but the same structure follows. Virtually polycyclic keeps good finiteness properties everywhere you needed good finiteness properties, is why that's the class of peripheral subgroups we used. And if you're a right-angled Artin or Coxeter group, there's an induction argument on the number of generators, and we use the free product argument, but with different base cases to do with direct splittings, or if you're neither freely indecomposable nor decompose as a direct product, you get trees in another way. And these all work for what we needed to do as well. Last but not least, some questions that I think might be quite difficult to answer, but who knows, maybe not. What about if the automorphism is exponentially growing? Maybe we expect to see some growth in these homologies. One reason to think that you should is that this tends to lead to the mapping torus being hyperbolic or relatively hyperbolic if you started with a hyperbolic group, say, and then you start running into these volume type questions. These are much worse defined, but there's reason to think there might be something here. Or a different question, sticking with a polynomial automorphism, if you change the normalization, so rather than taking logs and just dividing by the index, if you just took the size of the torsion part but divided by a polynomial of an appropriate degree, say, can you get a non-zero result out that way? Maybe, who knows? And that's the end. Thanks for listening. Let me know if you have questions. I'll find them and answer them.